Hello students, good morning. Today we are going to start new topic of this chapter, that is electric flux. So just let us have a look on the topic. Innate flux represents the flow, and if it is with the electric flux, it means the flow of electric field lines. In this way we can write electric field lines passing through any surface. It constitutes electric flux. Okay, in this way flux, that is represented by phi, it is directly proportional to the number of lines. So we can say number of lines passing through area. So in this way we can define the flux that is proportional to the number of field lines passing through the area. And if we are defining the flux and it is related to any area, then at the same time we can define the flux density. So we can say flux density, and it can be represented by D. It is as we are saying flux, here we are saying flux density, it is equal to the number of field lines passing through the area, that is flux, divided by the unit area, you can say. So in this way, number of field lines divided by the unit area, that is called flux density, that is represented by T. Okay, there are few things that should be remembered in the case of flux lines. For example, this is any surface and charges are distributed in it, and we have considered a small area in it, that is dA, and as we know the area vector is normal to the surface outwards. So this is our area vector. Here we can write AN, area vector, and if the field lines are passing in this direction, then from here we can define the component of these lines in the direction of area. Okay, so in this way flux is defined, the component of lines passing in the direction of the area. Okay, so first point should be, first point from here we can write, okay, that is flux is always normal to the surface. Normal to the surface means in the direction of the area, because area vector is always normal to the surface outwards. So first point should be clear from here, and if we find the component of this in the direction of normal vector, then we can say d dot dA. It is vector quantity, this is also vector. So this is the part of the flux. We can say the flux is equal to the dot product of the field lines and the area vector. Okay. After that, if the angle between these two is theta, then from here we can write d flux is equal to d dA cos theta. Okay, or without simplifying, just we can write total flux will be integration of this for full area. For this small area we have this flux, and for full area we will have full flux. So flux will be integration of d dot dA, we can say like that, and integration where? For full surface, yes, throughout the surface. So in this way we can find it is total flux is surface integral. Okay. Now considering a medium of uniform constant permittivity, means throughout the material the permittivity remains constant. It does not depend on the direction. In all the directions it is fixed. So in that case it is also known as isotropic medium. In this type of medium the flux density is equal to the epsilon times E. Okay, and we know E is Q by 4 pi epsilon R square, and from here epsilon is cancelled out and we can say D will be equal to Q by 4 pi R square. That is in the direction of E, because this is independent of the direction. So only this is having direction and this will be in the direction of that. So in magnitude D will be equal to this. What we can say, the electric flux density does not depends on the medium, because it is free from medium. However, electric field does, but density does not. Does not depends on medium. Now in one sentence we can recap. The flux is the electric field lines in the direction of the normal to the surface, and the flux density does not depends on the medium. Okay. After that we will discuss the Gauss law, and most probably all of us know about Gauss law, and we know that it is an alternate method to find the electric field in different cases. So just regarding Gauss law we can write one sentence. It is an alternate method determine electric field. P. Okay, so first point regarding Gauss law should be clear. It is, that is, this law is valid for closed surface only. So write down here, it is valid for closed surface only. And Gauss law states that the flux passing through any closed area is equal to the charge enclosed by that surface. So we can write it in the same form as flux passing through any area is equal to the charge enclosed by the surface. Enclosed by surface. So according to this definition, flux passing through any area, that is this, is equal to the charge enclosed by the surface. And the unit of charge is coulomb, so the unit of flux is coulomb also. However, if we talk about density, then coulomb per meter square. Now consider a case where a spherical body is there and this is the partial volume of the object, and consider a portion that is dA. The normal vector to this will be this dA. Okay, dA, it should be AN, by the way, AN. So in this case, according to the definition, the flux passing through this will be d dot dA, as we have discussed in the beginning, through the closed surface will be equal to the total charge enclosed by it. This is flux, that will be equal to the total charge enclosed by that, and total charge will be the volume charge density of this object for full volume. Okay, so this is volume charge density. We will integrate with respect to dV to get the full charge, then this will give us the full charge, and this is nothing but Gauss law. So we can say this is Gauss law. Okay, surface integral can be shown by 2 and volume integral can be shown by 3 integrals, so keep in mind. Either we can replace it by this and it can be replaced by 2 closed surface, so it's okay. This is the Gauss law. This is also known as the integral form of Gauss law. So we can write it, this is integral form of Gauss law, because use of integral to determine the Gauss law. Okay, due to the use of integration, it is named integral form of Gauss law. Now, if we apply the divergence theorem that we have studied in the beginning of the chapter, then we can say from here it can be transformed into volumetric form. Surface can be transformed into volume form, and it can be transformed like this according to the divergence theorem, and it will remain like that, rho v dv. This is according to the divergence theorem, and if we relate these two, then we find is equal to rho v. Here, due to the use of differentials, it is known as differential form of Gauss law. Differential form of Gauss law. So this is integral form of Gauss law, this is differential form of Gauss law. Now let us try to find electric field for different charges using Gauss law. So let us start from point charge. And we already have discussed the definition of point charge. So in finding the electric field with the help of the Gauss theorem, there are few important points. The first one is, it is mandatory to identify the Gaussian surface. This surface is chosen based on the electric field symmetry. So there is no need to write, just keep in mind the surface is chosen so that electric field symmetry exists. So for example, okay, it can be three type Gaussian surface. It can be spherical, and cylindrical for point charge, cylindrical for line charge or cylindrical charge, and cuboid. For example, consider a point charge, it is Q, and you can form a Gaussian surface. The most probable is, and the only possible is, the spherical surface. And in case of spherical surface, okay, x, y, z you can consider any surface here, ds, that is radial vector r. Now let us apply the Gauss theorem here. To apply the Gauss theorem, this is the direction of electric field lines and the electric flux density both. To apply the Gauss theorem, first of all we should find the area of this. So what area it can have? So this is spherical. So in case of spherical, to find the area vector in the direction of radial vector. So if to find the ds, dA means just ds, we should write dl first. From there we can find dl is, if we recall the coordinate geometry where we discussed the dl in case of spherical coordinate system, then it was dr in the direction of radial vector plus r sine theta, means this component, it was theta and it was phi. So we are not going to revise that, just I am writing here dl can be dr ar r sine theta d phi, r sine theta d phi a phi plus r d theta a theta. And from the differential length, if we wish to find the ds area vector in the direction of this, then we should do cross product of these two. So ds, or we can say dA, can be in the direction of this, can be multiplication of this and this, that is r square sine theta d theta d phi, and the cross product of this will give you ar. So dA can be r square sine theta d theta d phi in the direction of r, and we know that the charge enclosed will be equal to the, according to flux Gauss law, d dot dA. Okay. So in this direction, d is in this direction. We know that this should be in the direction of the normal to the surface, so in the direction of area. So d should be in the direction of ar. So from here we can see the direction of ar dot dA is this one, r square sine theta d theta d phi in the direction of, it is also in the direction of ar, and we have to apply for closed surface for area vector. Okay. So area vector can be written as, in area integral can be written as this with respect to theta and phi. We know that theta vary from 0 to pi and d phi vary from 0 to 2 pi. These things we have already discussed. So q can be written as, finally this term is constant, this is also constant, only variation is theta, sine theta and phi. So we can say dr into r square ar dot ar will give you 1 sine theta and d theta, it will give us minus cos theta, where theta varies from 0 to pi, and it will be phi, where phi varies from 0 to 2 pi, and from there we can say it can be equal to the dr r square cos pi minus 1 minus 0. So minus 1 it should be plus, no, minus times minus 1 minus 1. So it should be minus times minus 2, it should be 2. It should be 2 pi minus 0. So in this way q is this, and if we find dr, then we can say q by 4 pi r square, that we have already said in the beginning, that q d is independent of the material. So from here we can say d is equal to the q by 4 pi epsilon naught with the help of Gauss law. So we derived it with the help of Gauss law, and if we multiply it with 4 pi epsilon, if we r square, if we multiply with epsilon, then how much it will be? It will be equal to the E. So what we can say, D is equal to epsilon E, which we said in the beginning. So in this way we derive the electric flux density with the help of Gauss law and the relationship between electric flux density and electric field with the help of Gauss law. So for today we can stop at this point. From